Okay. Welcome back, everybody, to the afternoon session. So we'll be having two talks. And first, we are happy to have a mini course by Professor Matthias Reitzner. So he'll be giving one today and one tomorrow on random polytopes. Please feel free to interrupt with any questions. And also, if people attending online, also please feel free to interrupt or post your questions on chat. Okay, Matthias, over to you.
Thank you. First, thanks a lot for giving me the possibility for this talk. I'm very sorry that I cannot join you in person. I give two talks, and the first talk will be more or less very elementary, introducing some ideas and really working out things. And the second talk tomorrow will be more a survey on recent developments. So today I want to be really elementary, and please interrupt me anytime, and I will make a break in between asking for questions. So please. The title of my talk is Random Polytopes. So random polytopes deal with the following theme or subject. I have random points chosen to some arbitrary distribution. I will be more precise in a minute, and then I take the convex hull of these points. Then some of the random points are inside, some of the random points are on the boundary. They are the vertices of this random polygon in my picture, or in higher dimension random polytope. The question is, how does this convex hull look like? And the question is rather old. It goes back to Sylvester nearly 160 years ago. And he asked the following question. You have 4 random points in the planar case, so in R2. You take the convex hull of these 4 points. And now there are 2 possibilities what might happen. You might have 4 points like this. And if you take the convex hull, then it's quite immediate that the convex hull is a foregone. But you could also have the following situation, that you have 4 points like this. And if you take the convex hull, you have a triangle. And the question of Sylvester was, what is going on in the mean? So the number of vertices is either 3 or 4. And what's the mean value? And then there were several answers given to this question. I give the first 3 answers which have been given: 11/3, or this complicated fraction 48 times pi square, and so on, or the third 133 divided by 36. So people were interested in this question, tried to compute the mean value of the number of vertices, which is something between 3 and 4 clearly. And it turned out what people did and what was the reason for these different answers was that they had a different feeling about what should be random points. So the first value is due to Sylvester again, and he thought of starting with a triangle and choosing 4 random points uniformly in a triangle, and then the expected number of vertices is 11/3. But if you choose 4 random points at random in the unit circle, then the expected number of vertices is something else. That's the complicated fraction. This was computed by Woolhouse. And Woolhouse also computed what was going on if you start with a square and then you choose 4 random points in the square and how many vertices will occur in the mean. So from the very beginning, what people thought about this question is, if we choose random points somehow, then we should start with a convex set and then we choose the random points inside of this convex set. And this will be the subject of my talk. I have random points x1 up to xn, and they are uniformly in a given convex set K. And in my picture here, that's an ellipse, and I have random points inside an ellipse. And to make notations easier, I always will assume that the volume of this convex set is equal to 1. And then I take the convex hull of these random points inside. This gives me a polytope, or in the planar case, a polygon. And this polygon is clearly inside of K. And the question is, how does Pn look like? So this will be the question. And today in this first talk, I will always speak about the planar case. So I start with a certain set and I choose random points uniformly, which means independently, clearly, and uniformly with respect to the back measure. And then I take the convex hull of these points. And the most simple case is the planar, is the one-dimensional case. So I have a certain convex set. The convex set is given by this interval here. Interval always, or the only possibility for a convex set in R1 is an interval. I have an interval from A to B, and I choose random points inside. And I take, say, for example, the order statistic, x1, x2, x3. So I have in this example 8 random points. And the first question is, how many vertices does this have? So I take the convex hull. The convex hull of this thing would be the subinterval from x1 up to x8. And one would be first interested, what is the number of vertices? I will denote this by F0 of this polygon in one dimension of this interval. This clearly is equal to 2. This is trivial, this question. It always has the first and the last point with probability 1. So clearly it might happen that all 8 points are on the same point, but this happens with probability 0. So I always have 2 vertices. And the more interesting question is, what is the size of this missed area here to the left and to the right? And this is also well known. So the probability that x1 which is larger than a minus a is greater equal t. That's just the probability that all 8 points, or in general all n points, they miss this interval if this is t. So this would be b minus t divided by b minus a. That's the probability that all other points are on this side here. And there are n points, so it's b minus t divided by b minus a to the power n. And this is something you learn in the elementary probability course, that order statistic behaves like this. And if you know precisely this distribution function, then it's very simple to compute the expectation of x1 minus a. So this is the expectation of this length here. You have just to integrate from a to b this survival function. And this integration is elementary. You have b minus t divided by b minus a to the power n plus 1, and therefore you have a 1 over n plus 1 here, and a minus sign because you have minus t here, and then you have a b minus a here. So that's the the integral of this, and you have to evaluate it at a and b. And if you evaluate it at b, then you have b minus b here, and this gives you 0. So what remains is plugging in a, and then you have b minus a and b minus a. So this is equal to 1. So this is equal to 1. And then that's the outcome. So in the one-dimensional case, things are really elementary. You can by hand calculate it with your elementary probability theory.
No minus.
There's nothing.
No minus, right?
Plus. Thanks, yeah. Because a is the lower bound. Yeah. So the one-dimensional case is easy and trivial, and the interesting questions occur if you start to be interested in the two-dimensional case. Clearly, you have the same on the left-hand side here, and then you have two missing intervals to the left and to the right. Okay, so the one-dimensional case is trivial. The question is what is going on in 2 dimensions? And that was the picture I have shown you before. And one is interested in the number of vertices of a polygon, in the number of edges of the polygon, and in higher dimensions, clearly in the number of faces and facets. And one is interested in the volume difference, or in the planar case, in the area difference between K and the random polygon. And in higher dimensions in the intrinsic volumes, but I will not go into this today. I will mention this tomorrow. Why is one interested in these things? And the first motivation maybe is what I have shown you in the one-dimensional case. So we have used the order statistics. So when we were interested in the extreme points of a random sample, and this is something which is of interest, and the extreme points in higher dimension are just the vertices of the convex hull, and this will be of interest tomorrow in my second talk. Then clearly, if you choose random points inside a convex set K, this gives you a possibility to get a volume estimate. Think of K as being a very complicated convex set. And when you choose a random polygon or polytope in higher dimensions inside, then you have the possibility to compute the volume of this polytope. Clearly, this volume of Pn is always smaller than the volume of K or the area of K, and you are interested in the error which you make in this kind of volume estimation. And this touches the question about computational geometry, how to compute the volume of a polytope or of a polygon. And then there's also a connection to the optimization questions. If you're interested in the simplex algorithm, then you optimize some function over a polygon or a polytope. And the question is, how does a random polytope look like? What does the simplex algorithm for a random input? How complicated is it, and what's the running time of such a simplex algorithm? So there are several aspects or applications of these questions which somehow increase the interest in random polygons and polytopes. Okay, let's start with a very simple thing. I have n random points, and my convex set K here, this is equal to this is a ball. And in dimension 2, a ball is a circle. And since I want the thing to be of volume 1, I take the radius to be 1 over the square root of pi. So this makes my volume of my area of K of this circle equal to 1. And then I choose random points inside according to Lebesgue measure, take the convex hull, and I'm interested how many edges does this thing have? What's the expected number of edges? And recall that the expected number of edges is the same as the expected number of vertices, because when the planar case, we have as many edges as vertices here. So this is the same. And it's slightly easier to think of the expected number of edges. This is what we want to compute. So we check for each pair. So I take 2 points and check whether the connection between these 2 points gives me an edge. This is clearly not the case here. this is not an edge, but if you're lucky, then you have 2 points which are here at the boundary, and if you connect them, you really get an edge. So you just count for all pairs of points whether they form an edge or not. And clearly, all the points are identically distributed and independent. So you have n over 2 pairs in this setting. So you plug the expectation inside, and the expectation of the indicator function, this gives you a probability. So you sum up over the probability that all pairs form an edge, and you have n over 2 possible pairs here. So what you obtain is you just take 2 arbitrary points. For example, here's x1, here's x2, and you have to calculate the probability that these 2 points form an edge, and then you multiply by n over 2 because there are n over 2 pairs. And this is what you, in fact, you have to evaluate to get the expected number of edges. Okay, the probability is just the integration over the indicator function. So we integrate x1 and x2 with respect to Lebesgue measure over k. And then what you note is the following. If these 2 points here form an edge, so that this thing here, in fact, is an edge, then all other points have to be on this side of the line, which is, say, formed by an edge. If there would be 1 point at this side, then this would destroy this edge here. So this should not happen. And if we denote the volume or the area of this cap here, so we denote this by C plus, and we compute the area of C plus, and then the remaining area on the left-hand side, this is 1 minus the volume of C plus, because in fact, in some K has volume or area 1. So all random points except these 2 which form the edge should be to the left. And this is the probability that all other points are to the left. So x3 up to xn to the left. And this is why you arrive at this formula. So this is the analytic side. We fix x1 and x2, and then all other points have to be chosen to the left. And this happens with probability 1 minus this area of the cap. And this is what we have to evaluate. And there's a nice trick from analysis which helps us to evaluate this thing. So I have 2 points, x1 and x2, and they are on a line L.
Yes.
Yeah?
All the other points could also lie on the other side, right?
Yes, that's true. But now I fix some kind of orientation. Yeah. So yeah, in fact, you should have something like plus the volume of C plus to the power n minus 2. You're right, Carsten. Yeah. I will distinguish this because in the next step I will fix this line, and there are 2 directions from the line, and I will make both cases separately. Yeah. Yeah. Thanks. Okay, so there's now a trick from analysis. We are in R2, so we have a 2-dimensional point here, a 2-dimensional point here, so we have 4 coordinates. So in fact, this is a 4-fold integral. In fact, this is a 4-fold integration. And now we make a substitution of the variables by first fixing the line L and then taking 2 points here. And I will show you the result. The result is the following. I fix on this line L the 2 points. This is x1 and x2 again. Now, these are one-dimensional integrations. If L is fixed, this line, so these are two integrations. And then we fix the line L by, say, the normal vector u. And now we have to decide whether it's to the left and to the right, and this solves the problem Carsten mentioned. And then somewhere here is the origin. And then we take the distance of this line to the origin. This is what we do. I then note this distance by h. And each line is defined by its unit normal vector and the distance to the origin, which also can be negative. And these are the other two integrations. Yeah? So I had a fourfold integral before that, and now I have some kind of complicated change of variables, and I end up again with the fourfold integration. Now x1, x2 are one-dimensional integrations, h is one-dimensional, and u runs from 0 to 2 pi. That's just the angle. Yeah? Clearly, such a substitution has a Jacobian. You have to compute the Jacobian. And that's the complicated task here. And that's some kind of black box. I don't want to explain how this Jacobian occurs, but what is here, that's the Jacobian. And the Jacobian is just the distance between x1 and x2, because this is my far set f, my edge s, I should have taken. So f is just this thing here. And v1 is the one-dimensional length of f. So the Jacobian is just the distance between x1 and x2. That's the outcome. And that's not trivial. You really have to work for that. And I take it as a black box, that this Jacobian can be computed, and it's precisely the distance between x1 and x2. And now I have to tell you what 0 and L is. And if I have given this line L, I take this point to be equal to 0. And L is the length of the whole intersection of the line with the circle. And I integrate x1 and x2 between 0 and L. This is what I have to do. Yeah, so this is the same still. I didn't change that. But here I have to take into account the Jacobian. Which means I have the integral from 0 to L, integral from 0 to L. And then I have here something like x1 minus x2, dx1, dx2. And now we can calculate this by hand. Yeah, for example, we may assume that x1 is the larger one and the x2 is the smaller one. So I go here from 0 to x2. No, it should be like this. x1 minus x2 dx1 dx2. Now, so I get rid of this absolute value here. And now you can integrate this explicitly. And at the end, you get L to the power 3 divided by 6. That's the outcome of this integration. Yeah, it's really elementary. You just integrate it with respect to x1 first, and then with respect to x2, and the outcome is just the distance to the power 3 divided by 6. So let's have a look at this length. This L is just the distance between this point here and this point here. So this is just the length of the intersection. I take K, I intersect it with this line L, and then I take the length of this. This is just L. And I take it to the power 3. Yeah, so that's the outcome. So this Jacobian integrated twice gives you just the third power of this intersection length here, times 1/6. So at the end, we have this thing here, the 1/6 is here in front of this, and then we have this intersection length to the power 3, and then we have 1 minus the volume of this cap to the power n minus 2. This is only true if this cap is tiny. And I want to make the other way around. If we have a large number of points, say 1 million points, then this will somehow force this cap to be tiny. And we will concentrate on those part of the problem when this cap is tiny, and they will make this more precise, why this cap should be tiny. This is intuitively, it's clear that it must be tiny for a large number of points, but can we make this more precise? And the starting point for this is a formula of Schläfli, which is somehow very nice. You start with the origin somewhere, and then you take n linear lines or hyperplanes in R2 in general position. So what you do is you have your first line here, you have a second line here, you have a third line here. The question is how many cells does it generate? And this is quite immediate. Cell number 1, 2, 3, 4, 5, 6, 7, 8. Each time you have n lines, you have 2n cells. This is quite clear, because each time you plug in one additional line, you divide one of the cells into 2. Yeah, if I plug in the next line, for example here, then I split 2 cells into 2 and I add an additional 2 cells for that. So this is the formula of Schläfli, that if you have n lines, then you get 2n cells. And there's a generalization to higher dimensions, which is more complicated, but we will need it in the planar case. If I have n lines, I get 2n cells. This one should have in mind, because now what we want to do is we are interested in convex hulls. And the question is, I have somewhere random points chosen with respect to a symmetric distribution. And I have somewhere the origin. That's the origin. And the question is, what is the probability the convex hull of these blue random points is on one side of the origin, so that the origin is not contained in the convex hull, like in my picture. And there's a formula for that, and this formula is simple. What I do is I take the origin and it connects it to an arbitrary point. And if this point is the leftmost point and the other points are on this side, then the origin is not contained in the convex hull, because then the convex hull, it looks like that. Something like this may occur. So what's the probability that all other points are on this red part? Now what I do is for each of the points, for example, this point here, I have 2 possibilities. Either it's on the red part here or it's on the other part here. And if it's on the red part here, that's the probability that it occurs that it is on the right-hand side here. In this case, it's just 1/2, because my thing is symmetric. So the probability to be on the left or on the right side is 1/2. So the probability all other n-1 points are to the right. This is equal to 1/2 to the power n-1, because I have n-1 other points. And I started with taking one point and asking whether this point is, so to say, the first point which comes, and all other points are to the right in this direction. Now I have n possible choices for this point. With which I'm starting. So plugging things together, the probability that the origin is not contained in my convex hull, but that such a construction works, is n times 1/2 to the power n minus 1. And this is precisely Bendel's formula in the planar case. But it is more or less a simple geometric interpretation to get all points on one side. Again, there's something which generalizes this to arbitrary dimensions. This is shown here. It's more complicated again, but there's a simple geometric argument for that. Okay, I think Elisabeth maybe has already introduced the floating body.
Yes.
Yes, thanks a lot. That's perfect. So because I will now use this floating body somehow, I will use nearly the floating body. What I'm doing now is the following. I have a circle K, I have this cap, and these caps, they define a floating body. And what I'm using is not the floating body, but the cap here, but the double of the cap. So I take this cap and put it here on the other side too. This is what I call the Macbeth region. And I call it MX. So MX is this double cap. This is MX. And CX is this cap on the left-hand side. So I take this floating body construction, but I double all the caps. And the idea in the following is, if X is not contained in my convex hull, this is less or equal than the probability that X is not contained in the convex hull. And now I take all the points, random points, and dissect it with MX. So I take only the random points which are inside this Macbeth region, and I take the convex hull only of these points. And either X is inside or not. And if I have more points here outside, then the convex hull may somehow continue here. But say I get an upper bound for the probability that X is not contained, if X is not contained in these points only in the Macbeth region. So I concentrate on this Macbeth region. And this is nice because if I start with Lebesgue mesh on the whole circle, and then I concentrate only on the Macbeth region, then the Macbeth region is something which is symmetric. And now I can use the formula of Wendel. And the formula of Wendel says the probability that X, which is somehow replaces the origin, is not contained in a convex hull. This is just going back 2 to the power minus n plus 1 times n. And n is the number of points in this Macbeth region. Clearly, this number of points is random. So that's binomial distributed. I start with n points, and I look how many points are in this Macbeth region. Now, the volume of the Macbeth region is something which I fix. So that's the volume of the Macbeth region here. Just to make things simpler. So the volume of this is lambda divided by n. And this is a perfect choice for what I'm going to tell you. So this is a random number, and therefore I have to take the expectation of this. Okay, there's an elementary way to compute this expectation. If you have a binomial random number and you have to compute this expectation, you can do it. And the outcome is, I want to have a look. That's the outcome. It can be computed explicitly. And if n is large, then you see that that's the exponential occurring here. So this is lambda half e to the power minus lambda half. And the nice thing here, if lambda is large, then this tends to 0 exponentially fast. This means the question whether point x is contained in a convex hull or not, it depends on the size of its Macbeth region. If the size of the Macbeth region of the point x is larger than, say, a constant over n, say something like log n over n, then this tends to 0. So what I expect is vertices at constant divided by n. If you're really inside, say it's like log n over n, then the probability to be at the boundary or somewhere close to outside, this will not occur. So you really have to be somewhere by like constant n. And this is something which I will use, that this probability tends to 0 exponentially fast. Okay. For us, this means we can assume that this cap is tiny. All these caps are tiny. And therefore, instead of going from -1 to 1, we really can compute something like -1 plus epsilon. Yeah. We have to be close to the boundary. Now, everything is rotation invariant here. Therefore, if I integrate from 0 to 2 pi, if I rotate the whole picture, neither the volume of the cap nor the length of this intersection will change. So I can get rid of this integration here. This gives me an additional, this gives me an additional 2 pi here. And then I can take an arbitrary rotation, which brings it into a nice form. And the nice form is something like this. Yeah. This is my line L. This is the distance h, the height of my cap. And the radius is 1 over square root of pi. So this 1 over square root of pi minus h. And now I want to compute what this length of the intersection is. And then what I get here, I introduce a new parameter. So take this is x, this is y, and you're in a circle, so x squared plus 1 divided by square root of pi minus y squared is the radius squared. And this tells you that x squared is equal to 1 over pi minus 1 over the square root of pi minus y squared. And this is, okay, you can evaluate this. So this is minus is plus 2 divided by square root of pi times y plus minus y squared. And so if y is small, this is really very small. So the essential thing is that x squared is something like this. This means if this height is h, then this thing here, let's do it here, is precisely this. 2 divided by square root of pi times h to the power 1/2. You'll have to take the square root to get rid of this. Yeah. which means if you fix h, then this here, the length of this intersection is a constant, and this constant is twice the square root times h to the power 1/2. Yeah. Let me write it in this way. The diameter of my cap Cx, this is something like h to the power 1/2. This is the diameter. And the height of Cx up to constants is equal to h. And this gives me the possibility to compute this volume. We can do it explicitly by just integrating this function. And you can also get a feeling what it is about. You have the larger set would be this rectangle here, where you take height times space, which would be h to the power 3/2. And the smaller lower bound would be this triangle here. And this triangle is 1/2 of the rectangle. So you have upper and lower bounds of this order. And it is easy to see that V2 of C plus is up to constants. I should write C plus here. 3/2. So this thing here is a constant times h to the power 3/2. Clearly, I make some small error by ignoring this y squared here. And therefore, I will, in the following, write this thing here. This means it's the same up to small error terms. So this means is equal to plus smaller error terms. And here I have h to the power 3/2. Here I have h to the power 3/2. And now I have to integrate this. And the right thing here is to make a substitution. I put h to the power 3/2 equal to t divided by n. So h is equal to n to the power minus 2/3 t to 2/3, and dh is equal n to the power minus 2/3 t to the power minus 1/3 dt. So we really integrate this. So this is a constant times n is more or less n squared here. You integrate from 0 to something. And now we have 1 minus a constant times t divided by n to the power n. And h to the power, this is t divided by n. And here we have n to the power minus 2/3. 2/3. I plug it in this constant and make constant prime. T to the power minus 1/3 dt. And here if h is equal to epsilon, then t is equal to n times epsilon to the power 3/2. And so for n large, this gives me something like c prime n squared integration from 0 to infinity. And now for n large, this is just e to the power minus ct, because this converges to the exponential, times t to the power 1 minus 1/3 is 2/3 dt. And then you have n to the squared, n to the power minus 2/3, 1 n is here. So 1 n cancels out and it remains an n to the power 2/3. And this gives you this thing here. I have forgotten the minus here. Yep. And this explains why we expect n to the power 1/3 many facets or edges, and in the same way, in the planar case, the same number of vertices. And I was generous with the constant. I didn't follow all the steps, but you can calculate the constant explicitly. So at the end, you really have an explicit formula for the expected number of vertices and edges, which is of order n to the power 1/3. The second interesting thing, if you know how many vertices and edges are there, would be the volume or the missed volume. And there's a very nice way to link this number of vertices to the expected volume. And this follows from Efron's identity. So you start with the expected number of vertices and you write it in this way. So you check, I've forgotten the expectation here. You check for each random point whether it is a vertex or not. So you just take the probability that xi is a vertex. And now the thing is, xi is a vertex if xi is not contained in the convex hull of x1 up to xn, and here xi is missing. So in the convex hull of the other points. So here you have the convex hull of n-1 points. And clearly this probability is just the expectation of 1 minus the volume or the area of these n-1 random points. Because we take randomness with respect to Lebesgue measure. And this is clearly n times the same. So we get n times the expectation of 1 minus the volume of Pn-1. Or if we do it in the other way, we get the expectation of 1 minus V2 of Pn-1, or let's take Pn here, is equal n to the power -1, the expectation, that's wrong, n plus 1 to the power -1 times the expected number of vertices of Pn plus 1. So that's Efron's identity. It tells you if you know how many vertices are there, then you know the volume difference. The one here clearly is the volume of our convex set K. I have forgotten the square root of pi here. This is K. And this is n to the power -1 over 3, n to the power 1 over 3. And this here is an n to the power 1, -1. And in fact, you end up with n to the power -2 over 3 for this. So that's Efron's identity. And this somehow finishes what we were interested in. There's, say, a more or less elementary way, at least for the circle, to compute the expected number of vertices and edges, which is the same, and the volume difference. This was the more elementary part of my talk. Are there some questions?
In the,
See, this is the, yeah.
In the higher dimensional case, the only that will fail is the inequality between the number of expected number of vertices and expected number of edges.
Sorry, say it once again.
Efron's identity. So, so in this Efron's identity, it doesn't depend really upon dimension 2, except that the identity between the expected number of vertices and edges. That is the only place where dimension 2 is being used.
Yeah. So the simplicity here comes from the fact that in the planar case, edges and number of edges and vertices are the same. Yeah. In higher dimensions, it's more difficult. Yes. In higher dimensions, you have to compute the expected number of vertices separately, and after that, you can use Efron's identity. Yes.
Any other questions?
Okay, this was maybe the more classical part of the talk. Classical integral geometry, tools from analysis, simple tools from stochastics. And this was maybe the case until 10, 15 years ago. And then I would say heavy tools from stochastics have been introduced to this field. And in the remaining maybe 15, 20 minutes, something like this, I will explain what is going on in the, if you are interested in say, more distributional properties. What's going on with variances? What is with central limit theorems? And the variances have been a long-standing open question, and they are now settled more or less. And central limit theorems, the right tools for central limit theorems have been developed, I would say, in the last years only. And I want to show you somehow what is going on. And in the second part, I don't want to be so precise as I have been in the first part. So for the variance, it turns out that we are not able in most cases to really compute it explicitly, except in the last years where tools have been developed which are really complicated. But there's a more or less simple way to compute, say, an upper bound, which tells you what the size of the variance is. And the right tool comes from statistics. It's the Efron-Stein-Jackknife inequality. So we have n+1 random points here, or random variables. And I have a function s, and s only depends on n random variables. Which means I have n+1 random variables, but I need only n of them. So I can say, for example, ignore x1 and just evaluate my function s for x2 up to xn+1. Or I could ignore x2 here in the second case here, and then I take the function of x1, x3 up to xn+1. So since I have n+1 random variables, I need only n of them. I can ignore either x1 or x2 or x3 up to xn+1. So I get n+1 possibilities to evaluate my function s. So for s1, I ignore x1. For s2, I ignore x2. And then I take the mean value of all these s1, s2 up to sn+1, and then note this mean value by s bar. And the Efron-Stein-Jackknife inequality tells you if you're interested in the variance of the functional s, then it's upper bounded by expectation of, and now you take the difference between si and the mean value. That's the Efron-Stein-Jackknife inequality. There are several proofs now available. It's not completely very complicated, but you have to do something, and we will use it as a black box. This was proven by Efron and Stein, and we use it in a certain form here. And the right way to reformulate the Efron-Stein-Jackknife inequality here is the following. If you take this sum here and you want to minimize it, so we have numbers Si, and we are looking for the value of alpha which minimizes this sum, then we minimize this sum if alpha is just the mean value. That's the minimizer. This is well known from analysis. And this is often used in stochastics. It's minimizing the square. Which means in the Efron-Stein-Jackknife inequality, this is on the right-hand side. And this is the minimum over all these terms. And if we take one alpha, which is not the minimum, so we plug in some other alpha, whatever comes to your mind, then you get something which is bigger. So we replace the minimal, the optimal alpha in the Efron-Stein-Jackknife inequality. So this minimal alpha here is S bar, the mean value. We replace it by something else. And what we do, what we replace it is, in our case now, if we come to random points, then S is the number of vertices of the convex hull. Then we replace the mean value by the number of vertices if we take all n+1 points. So this is equal to our alpha. So we take the original Efron-Stein-Jackknife inequality, but we replace the optimal S bar by not the mean value of all possible vertices if we ignore one of the points, but we take the convex hull of all points and take the vertices of that. Count the vertices of this. And the same holds true for all other functionals like the area difference. So if you want to get a nice upper bound for the variance, what you have to do is add one additional point. You have n points, n random points. You want to say something about the variance of these n random points. Take one additional random point and have a look at the effect. This is the idea behind the Efron-Stein-Checkner inequality. What is the effect of one additional random point? And now there's one thing, so you compare n points to n plus 1 random points. If xn plus 1 is contained in Pn, then this has no effect. Because then you have your random polygon somewhere, and you add one additional random point inside, then Pn will not change. In this case, Pn is equal to Pn plus 1. Pn will only change if xn plus 1 is not in Pn. That's the only chance that something is changing. So the question is, what's going on if we have this situation? This is Pn, and here is xn plus 1 outside of Pn. So that something, if you take the convex hull now, then something will change. That's the question. And now I will somehow cheat. So the disadvantage of this thing here is that you have something like this here, and you have this indicator function here, and they clearly they are linked. The things to the left and these terms are not independent. What is easy to compute is something like this. This would be easy, but we don't have that. If these two things would be independent, then this would be the outcome. And now the first step I'm cheating is that I act like both things are independent, because this gives you already the right idea. Yeah? What's the probability that xn plus 1 is not in Pn? That's the probability that xn plus 1 is a vertex. Of the new set. Or to be more precise, that's the expected volume of Pn. 1 minus the area of Pn. Because xn plus 1 is distributed according to Lebesgue measure. We have just computed this expected volume, or this expected area difference. It was n to the power minus 1 over 3 or 2 over 3, 2 over 3. And now you have to compute this. This is some kind of integral geometric evaluation, which is long, but it's not very complicated. It turns out that this is more or less a constant. That's somehow surprising. One has to really compute that to see that this is not going to infinity. So if you plug in one additional point, then this is the typical situation. You have here one edge, and it's just above. Maybe also this situation occurs. This is your random polygon. This is your new point. You have something like this. So you see either one edge or 3 edges, something like this. But what will not occur is, with high probability, that you see thousands of edges. So your additional point is very close to your boundary. So the additional point sees one edge or 2, maybe 3, and that's the end. Therefore, this is constant. And so what we obtain is the variance of the number of vertices of Pn is bounded by a constant times we have one n here, Here we have times n to the power minus 2 over 3 is a constant times n to the power 1 over 3. This is the outcome. And I was cheating here because these two things are not independent. And I didn't show you why this is constant, but this is the outcome of some integration formula. That's the Efron-Stein-Checknov inequality. It gives you more or less simple tool to develop that. And what you do, in fact, is you really take the whole thing here. So everything here. And write it as an n-fold integral. And then you really evaluate that. This is complicated, it's hard, but then you get rid of this problem that here you have to use the independence, which is not true. Okay, without going into the details now, but maybe this gives you an idea why n to the power 1 over 3 is what we expect for the variance. So the result is really, in fact, that the variance of the number of edges, which is clearly the same as the variance of the number of vertices, this is of order n to the power 1 over 3. And then there are lower bounds available at the moment, which tells you that this is in fact of the right order. So we have upper and lower bounds, which tells you that this Efron-Stein-Checknov inequality, this is really sharp. Yeah, in all cases, I know this Efron-Stein-Checknov inequality already gives you the correct order. Okay, this is a way to get, say, at least bounds for the variance.
Matthias,
Yeah.
is it possible to say anything how you derive the lower bound?
To derive the lower bound, you have to first you have to split the variance. So you introduce nice configurations, and then you compute the expectation of the variance of f naught of Pn given that this is a nice configuration plus the variance of the expectation. And you know the variance is always greater or equal to 0. So this is always greater or equal just the expectation of the variance of f naught of Pn, given that this is nice. And now you have to, I have to tell you what nice is. Yeah, and nice is the following. I fix a cap. It should be much larger. And in this cap, I fix 3 balls. 2 points here, 1 random point here, 1 random point here, all other random points here. I fix this part here and let these 4 points, say, floating in these small balls. And then the number of vertices is either 3. If these 2 points are in a position that the convex hull is just looks like a triangle, but it could well be that this is something like this. And then you have 4 vertices here. And this special situation suffices to show that the lower bound is of the right order. You just have to make this precise. And then you use again the floating bodies introduced by Elizabeth. So that this cap is a cap of the defined by the floating body. But you have to choose everything in the right order, which is not, so it's not too complicated, but it's not obvious. You have to think a little bit of the size of the small balls and of the caps.
Okay.
Okay. I think I'm nearly running out of time, so let me just make a small remark about the central limit theorem. Yeah, a central limit theorems. There are now several ways to proving central limit theorems for this question, and the most recent is the central limit theorem for stabilizing functionals. And I just want to explain to you what a stabilizing function and the score function is, because this stabilizing functional CLT is for score functions. So you have f, a function which, so chi n always stands for x1 up to xn. And you say that this function is just a sum, where for each of the xi's you check whether it, say, contributes to f or not. And the contribution, it clearly depends on the position of xi with respect to all other points. So, and this contribution, this is what they call the score function. In our case, say, if we are interested in the number of vertices, then the score function is just checking whether xi is a vertex with respect to all other points. Clearly, this depends on the position of all other points. So this would be the score function here.
Can you ask him to repeat?
Matthias, can you just repeat the slide? Matthias, can you hear us?
Yeah.
Can you just repeat what you said earlier? I think you are frozen and we didn't hear you.
Sorry. Yeah. So the function f, it depends on x1 up to xn. And then I just check, and this is the score function, what is the contribution of x1, what is the contribution of x2, what is the contribution of x3 for my capital F. And if I can write it in a way that here I have a sum over all these contributions, then this is called a score function, or the sum of score functions. And this is what the CLTs are dealing with. And in our particular case, if we're interested in the number of vertices, I just check for each of the points x1, x2, x3, whether it's a vertex or not. And if it's a vertex, then the score function is equal to 1. And if it's not a vertex, then the score function is equal to 0. So this would be, for the number of vertices, the score function is just the indicator function. And these CLTs for stabilizing functions, they deal with score functions, which are somehow nice. And what they need is that the score functions are stabilizing, which means the following. I have my point x here, and I have all the other random points. And stabilizing means that okay, that's nearly what I wanted to have. So my x is here in the middle. I take a ball around my x of a certain radius. And the score function is stabilizing if the following happens. If I fix everything in the red ball or red circle, then what is happening outside does not influence my score. And for the vertex, this means this is a vertex if I can take a huge ball. That's not the right thing. That's not a good ball. Yeah, okay. It should be a ball around with center in X here. This should be the center here. So this should be X. This is the center. If I fix what's happening here inside, and the points outside will not play a role, then I'm satisfied. And this occurs if the following is happening. Here I have my vertex X, here I have the next vertex, and so on. If I fix the next vertices here and here, then what's going on here will not influence whether it's a vertex or not. somehow. The situation is more complicated because they need 8 additional points which may float freely. But the idea is, if you fix a surrounding of your vertex, which is sufficiently large, then the thing is fixed by the surrounding. And if you're far away, this will not influence what's going on. This is an essential ingredient here. And this clearly is true if you're looking for vertices in a circle, something like this. You have to determine the radius of stabilization. And this can be done. And the radius of stabilization is exponentially decreasing, and this is the decrease. This is something which can be computed using the floating body, which was introduced today. So this would be the first ingredient. The second ingredient is you have to show that the question whether the point is a vertex or not, it depends on the distance to the boundary. And here again comes the floating body into the game. You have your circle, you have the floating body. The random polytope is somewhere in between. If you are far away inside, then you can't be a vertex. So the probability that something is a vertex, this will only occur if the distance to the origin is small. And if the distance is increasing, then the probability that this is a vertex, this is decaying exponentially fast. So this is the second ingredient one has to prove. There's a third ingredient, which is just a computation of a certain integral. And then at the very end, if you have check these 3 points, then you get a central limit theorem. And this is due to Reitzner and Matthias Schulte and Joe Jukic. And the nice thing about the CLT is that this is optimal here. So a CLT in most cases is optimal if the error term with respect to Kolmogorov distance is 1 over a constant divided by the square root of the variance. So this is just a short glimpse on how CLTs can be proved in this setting. Okay, sorry for the last part, which was really very, very sketchy. Yeah. Okay, I think that was it. Thanks a lot.
Any questions? Matthias, 2 things. One is there a score function for volume? Clear?
Yes. So for the volume, you take a score function. You have something like this, and then the continuous, and somehow you split the volume difference like this. And to each vertex here, you take half of that. Clearly, the score function, it depends on the next vertices, but the score function might depend on all other points also. And also this is stabilizing. If you're far away, then this would not influence the shape of the polytope close to this vertex. It's more complicated for the intrinsic volumes. Then you really have to work with other tools.
And in the variance bounds, do you have more precise constants?
Yeah. More? So I will mention this tomorrow in my survey talk. We know much more in the meanwhile. But also this is, say, recent, the last maybe 10 years. Yeah.
Okay. So if there are no more questions, we will thank Matthias once again.
Thank you.
We see you tomorrow at the same time. I think you all will. Yes. Can you Matthias, can you hear us?
Yes.
Okay, so then tomorrow we'll see again at
Yes.
before.
Yes.
Yeah. Thanks a lot.
See you.
And is it okay? Can you share your slides with us and we can put them on our website? Can you share your slides with us? We can then put it on our website. Okay.
Yes.